Okay, guys, so let's quiet down on the homework. Number one, really quick, was a concept-y one, so let me talk about that really fast. So number one says any object that's going in a circle is accelerating. Yes? I'm doing this from memory. Yes. Here we go. How do we know this? So the answer was on the sheet, but so one of the things we learned several chapters ago is that there are three ways of accelerating. Okay, what one thing has to happen if you're accelerating? Sure, we got it.
A change in velocity.
Good, you have to have a change in velocity, right? So up until this chapter, all of our changes in velocities have been about changing your speed, right? Either going faster or going slower, right? Okay, but remember, we learned that there are three ways to accelerate. You can speed up, slow down, or we got change your direction, right? Because if you change your direction, you're changing your velocity, right? Because going that way at 10 meters a second is different than going that way at 10 meters a second, which is different than going that way at 10 meters a second. Okay? So automatically, just because the thing is going in a circle, it has to be accelerating. And in 5.2, we're going to learn, what does that mean? What causes a thing to accelerate? That we just took a test on, sort of. Force, right? So 5.2 is about the force that causes the circular motion. Okay? So that's that. So what I tend to find is the hardest part of this, you guys, is not the math. The hardest part of this is sort of, I guess, interpreting the information, really. Like figuring out what the given information tells us and figuring out what's being asked for. All right? The single most important thing that you can do at this point is please, please, please make sure that you have a really good understanding of the difference between this guy and this guy. All right? So in the video, I gave you the equation, F equals 1 over t, I think was the equation I gave you. All right? I'll be honest with you guys, I almost never use that equation. Okay? Because in order to use it, you have to know either the frequency or the period. Okay? So let me come back to that equation. Let me really quickly talk about definitions. All right? Period. What's the symbol for period? Like velocity is v, force is f, period is capital T. Why is it a T instead of some other letter, like B or something?
Time.
Good, because it's a measure of time. Okay? So in the video, I was spinning, or 5 years ago, me was spinning the V around, right? And so he went around in a circle, right? And so the period represents what about the V's motion? The time
it takes for one complete rotation.
The time for one complete revolution, rotation, cycle, whatever, right? So this is the time for one repetitive motion. I think in the video I probably said rotations or revolutions. Later on we're going to do waves, okay, which isn't really about revolutions or rotations. It's about, you know, a particle oscillating up and down. But it's a repetitive motion again, right? Follow? Okay. So what are the units going to be? Because we're measuring time, the units are going to be
Seconds.
Seconds, right? So if I say the period is 4 seconds, I'm telling you it takes 4 seconds to go around once. Very frequently, though, we write it as seconds per rotation, revolution, whatever. Okay? But saying per rotation is a little redundant because it's implied by the definition. Cool? Yeah, question?
Oh, so isn't just the easy way of taking like time for spins? Or like,
Yeah, totally. Yep. All right, so everybody good with that? All right, how is frequency different? It doesn't measure time.
Measures distance per revolution.
Distance per revolution is something different.
No.
That's okay. That's good. That's why we're here. That's why we're having these conversations. Where'd my tennis ball go? There it is. Distance per revolution is a different name,
oops.
which you should be aware of. So if I spin this tennis ball around, I don't know where my B is.
Right here.
Where is it? Oh, he's over there. Okay. So what's the distance per revolution? There's a word for it. One word. Circumference, right? It's the circumference of the circle, right? Right? It's the distance it travels as it goes around once. And the period is the time per revolution. So what's the frequency? How frequently did I talk about this in the video? Here's a simple example if you forgot. How frequently do you brush your teeth? Twice per day. You're telling me how many times the thing happens Wait, you didn't just tell me how many times you've brushed your
Per
teeth.
unit of time.
Per unit of time, right? How frequently do you brush your teeth? Twice per day, okay? How frequently does this go around? Some number of times per second, or per minute, or per hour, or whatever, right? That would be the frequency, right? So my frequency is the number of cycles, the number of revolutions, the number of rotations, or whatever, per unit time. Okay? So really quickly, and then I promise I'll get to the homework. So in the video, we looked at Buzzy the bee, and we discovered that he completed, was it 10 revolutions in 8 seconds, or other way around?
8 over time.
10 revolutions in 8 seconds.
10 revolutions in 8 seconds. So 10 revolutions is the same as 8 seconds. Okay? So, Weston, the reason I didn't react to what you said is because you said 10 over 8, but what is that? Is that? So this is a thing, and this is a different thing. One of those two fractions is the period, and one of them is the frequency, right? So which one's period, you guys?
8 seconds.
8 over 10, right? Because that's the amount of time per revolution. Cool? All right? And that means that this must be the frequency, right? Because I'm telling you how many times it goes around per unit time. Follow? What do you call it when two fractions look the same but they're flipped over? What's the word for two fractions that are like that? Inverse or reciprocal, right? So, a few minutes ago I alluded to this equation. How do you find the reciprocal of a number? Yeah, you just do 1 divided by that thing, right? So all this equation really tells you is that frequency and period are reciprocals. Okay? So, long story short, to find frequency or period, you really are better to understand these two definitions thoroughly. Cool? Alrighty, so that was the general talk I wanted to have. Do you guys have specific questions you would like me to go over? What do we got? Sure, Weston. I need to have a rule against having rhyming names in the same class, because it's totally messing me up with Weston and Destin. Anyway, go ahead, hi.
So when you have like planets, is the furthest one going at a faster velocity is the radius?
Okay, good question. So you're saying the one that's farther away has a bigger radius. So finish that train of thought. Why does the bigger radius matter?
Well, when you plug in the equation, a bigger R is also a bigger V.
Okay, cool. What equation are you talking about?
I don't remember, but it's V.
Okay, so in the video I showed you guys two equations for velocity. 2 times pi times radius divided by period, right? Did you guys realize this is just distance over time, right? This is the distance traveled in one rotation divided by the time for one rotation, right? Okay? And remember, 1 over t is the same as frequency, so this is the same as this. So Weston, if I'm understanding you right, what I'm hearing you say is, if you increase the radius, that's going to increase your velocity, right? I agree with that, but you haven't looked at everything. What else do we need to consider?
Wait,
How frequent?
Yeah, you got to look at the time it takes too, right? Or how frequently it occurs, right? Okay, so yes, is it Mars and Venus, is that right? So Mars is farther away, so it's going to have to travel a bigger distance to get around the sun, right? Okay, but just because it goes farther doesn't mean it's going faster, does it? Right, like if I give you car A, and I tell you car A just went 10 miles, and car B over there went 20 miles. Does that mean it went faster?
No.
No, because you got to ask yourself about the time, right? So the idea for that problem, the Mars and Venus one, is this. Mars, because it's twice as far from the sun, it's going to go 2 times the distance each year, right? Each orbit, right? But Weston, what does it tell us about the time? It says a year on Mars.
I don't have it in front of me.
Okay, somebody help out.
3 times as long.
Yeah, it tells you a year on Mars is 3 times as long as it is on Venus, right? So a year is the time it takes for the planet to go around once, right?
So you're dividing by 3.
So Mars goes 2 times the distance in 3 times the time. So is Mars going faster or slower?
Slower.
Slower, right?
Um,
Do you see why?
because that's like 0.67.
Yeah, exactly. For them to have the same speed, it would have to go twice the distance in
Like,
twice the time, right? Wouldn't that be the same speed? Because they're proportional? Okay. So yeah, I mean, some of these problems are tough because they're really concept-y. That's a good example of one of those where there weren't really numbers that you could use and you just kind of had to
Yeah, I
go.
just wasn't sure like which is more of a factor, radius or time.
Okay, so which is more of a factor, radius or time? Well, so your velocity is directly proportional to the radius
Yeah.
and inversely proportional to time.
Okay.
Okay? But since neither of these are squared, they sort of count the same amount, you know?
Sure. Like if you divide by bigger numbers, it'd be smaller, and if the bigger number on the numerator is bigger.
Right, yeah. Yeah. All right, did that problem make sense, you guys? What number was that? That was totally number 12? Okay. Everybody cool with 12? AJ, you had a question. Was it 12 related or other related? No. If you got a question, ask it. Huh?
I kind of just got answered the question.
Okay. All right, yeah.
all right, so I just got a little bit confused on number 3C.
Gotcha. Okay. So before I do 3C, was everybody good with 3A and B?
I was just confused about, like, if there was an equation to plug it into, or if it was just
No,
like
and
a
this is,
concept. Or...
it's just a concept.
Oh, okay.
And this is what I was saying about understanding period and frequency. So give me 2 seconds. Is everybody good with 3A and B? Going once, twice, sold. Okay, so 3, C, and D. So check it out. So in number 3, here's what we figured out. In part A, we figured out that the period of this spinning ball is 0.20 seconds. And we figured out that the frequency was 5.0 revolutions per second, or if you want to say 5.0 hertz, that's cool. Okay? C says, how many times will it spin in 12 seconds? C. How many spins in 12 seconds? All right. So there are a few ways of doing this. Okay? So one way to do it, and this would probably not be the way that I would recommend, but it does work, so let me just show you real quick. We know that we completed 15 revolutions in 3 seconds, right? So we can just set up a ratio. 15 revolutions is to 3 seconds, as x revolutions is to 12 seconds. Does that make sense?
Yeah.
Everybody? So that works, but that's not my favorite solution to this. So, Ethan, I'm going to pick on you for a second here, and everybody needs to understand this. So, talk to me about what these things mean. The period is 0.2 seconds, so what does that mean?
That's like the time to complete one rotation.
It's the time it takes to complete one rotation. So if it takes 0.2 seconds to complete one rotation, how would I figure out how many rotations you get in 12 seconds? AJ? Multiply? So let's see if that works. So if you multiply 12 seconds times 0.2 seconds per revolution, does that give me the right units?
And by 5.
Say it again?
Multiply them.
Okay, yeah. So I'll get to that in 1 second. So what I was thinking was that if you divided by 0.2 seconds per revolution, that works. All right? But I like AJ's solution the best, which is this. Look. This number tells us that you complete 5 revolutions every second. 5 revolutions every second. So in 2 seconds, you'd complete 10. In 3 seconds, you'd complete 15. And in 12 seconds, you'd complete, well, I don't know. Let's do that. Let's see. 12 seconds times 5 revolutions per second. Notice, it's just, what do you guys call this? Dimensional analysis? What happens to the seconds? They cancel out. Hooray. And I get 60 revolutions. Does that make sense, Ethan?
Yeah.
Everybody? All right, and then part D is similar. How long will it take to spin 89 times? Well, how long does it take to spin once? Look at the numbers, you guys. How long does this thing take to spin one time?
0.2 seconds.
0.2 seconds, right? So to figure out how long it takes to spin 89 times, you just multiply. 0.2 times 89. Make sense? All right. Questions on that? All right. What else? Yeah.
7.
7. All of it? That's fine. If
I
okay.
didn't really understand. I tried to like find the circumference, and then I got like a different answer.
Okay.
So yeah.
Okay. So number 7 says the Earth spins around once per day and has a radius of 6.38 times 10 to the 6th meters. So radius equals 6.38 times 10 to the 6th meters. What is that? It spins around once per day. What's that telling me, you guys?
It's frequency.
It's no, it's T.
Time.
Period.
Period. Yeah.
So it could actually be either, right? What it's telling you is that it spins around once per day, right? So it's telling you that one rotation of the Earth takes 1 day, right? So my period is the number of days per rotation. So 1 day in one rotation, right? And then, so that's 1 day, right? That's your period. And then just because we usually work in seconds, I converted that to seconds. So multiply by 24 hours, multiply by 3,600 seconds, and you get 86,400 seconds, just by doing, dimensional analysis. Good? So that's question A.
Oh, so it's all you do. You just convert it. Oh wait, I actually tried to do that, but how was
Do you want me to do the factor label?
No,
Or the?
I did it, but I probably just like typed it
Okay.
wrong.
All right, so that's part A. Part B wants the frequency. Once you know the period, this is, I think, the only problem on the whole assignment where I actually used this equation. Once you know the period, how do you find the frequency?
F equals 1 over T.
Yeah, they're reciprocals. So F equals 1 over T. So 1 over that. And it gives you like 0.00095 or something like that. Is that the right number? I did that from memory.
I don't think so.
No?
I mean,
Pretty much. Okay. Somewhere in that neighborhood. All right, cool? All right. Now, questions C and D ask about the velocity of a person at the North Pole and the equator, okay? So let's let this line represent the equator. So I'm going to spin it this way. Okay? So, which one is C the one that's equator, or
C is
That one's the
North Pole.
C is North Pole? Okay, so. Okay, so that X there represents the North Pole. Oh, it's off center. That's terrible. Who built this basketball? This is why I don't play sports.
Why don't you just make that?
No!
Okay.
All right, so here it is. There's the North Pole. That X right there, North Pole. Good? Why am I making this so difficult? I don't know.
That's what I was gonna say.
I know. Okay, so here's the North Pole. You ready? How fast is the X moving?
It's not.
It's not, right? Because what's the radius?
0.
The radius of rotation is 0, right? Does that make sense? It's like standing at the very center of a merry-go-round.
Wait, what do you mean the radius of rotation?
So,
You're just like.
yeah, it's just spinning in place, right? You see, is the X, the X is rotating,
Yeah.
but is it moving? Nope. Cool? Now, if that same X is at the equator, now that X is moving, isn't it?
Mm-hmm.
Follow?
Yeah.
So to do part D, so C is just 0.
You just plug it into the.
And then to do D, yeah, you just go, oh, well, V equals, and I used this one, 2 pi r over T, just because the T is easier to deal with than that stupid frequency.
Okay. Thank you.
Does that make sense?
Yeah, I understand that.
Everybody good? All right, what else? There was one question about the scratches on the record. This is a test question. So you got to be able to find the velocity of the 2 scratches. That's basically just, using some version of this equation. I like the question, though, and I want to make sure you guys understand it. So let's see, what number is this? I guess it's 2E. Number 2 got hole punched out. So number 2E, how can two scratches on the same record move at different speeds? So, somebody want to take a stab at answering that? Sure, what do you got, Ethan?
All right, so basically what I said was the two scratches can move at different speed because the scratch, wait, hold on. The scratch 2 inches away from the center is traveling less distance per revolution. And wait.
Yep, you're good, you're good.
And the time to travel 1 revolution is equal to the other edge, which has to travel a greater distance in less time.
Good. Wait.
Wait,
I agree with everything except for the second to last word.
Equal time.
There you go, equal time. All right, so this is sort of like the planets problem, right? The difference is the two planets aren't connected in any way, right? So their time is not the same, okay? So if this is a record, and the pieces of tape here represent scratches on the record, okay? As the record spins, during the time it took for that record to spin once, this scratch went all the way around, and this one went here a smaller distance, right? Okay? So here's the reason I call attention to this problem, and you nailed it, but a lot of times people skip part of it. You can't just say that the scratch on the outside goes a bigger distance. That's only half of a correct answer. You have to say in the same amount of time or with the same frequency or something like that. You have to tell me something about the time or the frequency with which they rotate or at which they rotate. Okay, Weston?
Is that why the track is scattered?
Yeah, and that's the last one of the questions on there, right? That's why the starting lines, if you run track, the starting lines at the outer edges are farther ahead because it's a longer distance around.
So if 4 people are running at the same speed, in 1 second they both get to the same spot, or like if they could run that fast.
Yeah.
Okay.
Yes.
Okay, so this is a little bit unrelated, but so like on a record, since like the record itself on the outside it's moving faster, so when the arm comes down with the needle and it's on the outside, does that mean the grooves on like along the outside would have to be like a
They're
different
farther apart.
size?
Yeah, they're farther apart,
Okay.
like the bumps or whatever they
Yeah,
are have
or
to be
else the
farther
sound
apart
would be
against that
distorted.
edge. Yeah.
Right. Okay.
Yeah, exactly. So, I mean, the idea is they press those records using a process that's very similar to the process that they used to play it.
Oh.
Do you know what I mean? So they spin the record and they cut the grooves.
Oh. Yeah.
Do you know what I mean?
Yeah.
And then when you play it back, so,
Okay.
yeah.
So basically, the tape on the outer ring goes faster because it has to like go around longer distance, like with like be there at the same time,
Yes.
right?
Yep.
So then the one, that one's slower speed.
Yes.
Okay.
But same frequency, right?
Yeah.
Make sense, you guys? All right.
Can you think about it in terms of radius?
Can you? Is that what you said?
Yeah.
Sure, but again, that's only half of it.
Okay.
Right? For the same reason as the planet thing. You also need to tell me something about either period or frequency. Follow? All right. Is there any concepts we didn't hit that you guys would like to discuss? Did everybody figure out there's one problem about a race car going 30 meters a second and you were given the radius of the track and you had to work backwards and find either the period or the frequency? Everybody figure that out? Okay. All right. Any other questions on the homework? All righty. Cool. So, the other day, you guys did a practice SAT thingy. So why don't you guys dig that out?